Thank you. Great, can you hear me? Yes, good. So my name is Erik Landolsi. I'm currently the VP of Future Labs at Irisity. That is the department that does our most kind of forward-looking, research-oriented stuff. I was previously the CTO as well, but that changed when we merged with another company right before Christmas. I will tell you a little bit about that as well. My own background is as a PhD within computer vision and machine learning from Linköping. I did that back in 2008. So I've been working in the industry since then with computer vision, machine learning stuff from before deep learning was cool until now, basically. I'm going to talk about some privacy aspects of what we do at Irisity regarding video analytics. Where do you point this? There, okay. So first, some overview of the company. So current company Irisity is actually a merge between two more or less equally sized companies, Irisity and Agent VI, that was merged this fall. Now we are approaching almost 100 people, spread out in 5 countries with main development offices in Göteborg and right outside of Tel Aviv. So roughly equally sized departments there. We're about 40 people in R&D, and then we are some sales engineers, salespeople, finance, and the usual stuff. We are listed at Stockholm, so we are a public company, still scaling up, I would say. The main product is called Iris, and the idea is to use real-time video analytics to react on unwanted events for safety and security applications. So typically like this, you have a bunch of cameras somewhere in the world, and connect our software to it, configure some rules for what you want to detect in real time, and then when whatever you want to detect happens, we send a 7-second clip or 10-second clip to some operator that can take action of what happened and do something like send a guard, stop a metro train if someone is walking on the tracks or anything like that. So the stuff that we can look for is lots of different stuff. We can look for violent behavior, people fighting, we can look for fires, we can look for people running on railway tracks, we can look at unattended objects that could be suspicious bombs and so on. So, for example, as one example, we have an installation right now in Stockholm subway where we're looking for people on the tracks, and we are extending that to also look for suspicious bombs, bomb bags and stuff like that. So far, we have saved at least 3 lives in the Stockholm subway since this fall for stopping potential suicides where they could stop the train in time. That's quite important stuff. But I'm here today to talk about privacy, and since we work with surveillance cameras and security cameras to some extent, maybe privacy is not the main word that you think about. So why does privacy matter in a business like this? Well, there are a few factors. So, of course, the boring part is the regulatory factors. So now we have regulations like GDPR in Europe. More and more countries are also starting to think about these questions. So some cities in the US have started to ban facial recognition, for example, to improve privacy. So we have to consider that, of course, when we develop our systems. There are competitive factors. So there are nowadays huge companies in countries like China, for example, that are maybe 10 times or even 100 times as huge as our companies that do this like city-scale surveillance of more or less everyone that lives in a city. And that is not how we want to do it. We want to do it in some different way to find our niche in the marketplace. And there are, of course, motivational factors. I think it's more fun to work with this kind of technology if you treat privacy with care and do this in a good way. So this whole thing boils down to how can we develop and operate a large-scale video analytics platform while maintaining some kind of privacy or as much privacy as possible for monitor individuals. And I will touch upon a few aspects of this. And the first aspect is training data. And I will here start with a case study. One of our more recent algorithms is detecting people falling down to the ground or lying down on the ground. That is applicable for hospitals, elderly care centers, for example, when you have sick or elderly people that can actually be monitored in the places they live in these facilities. And there, of course, privacy is very important. They don't want anyone to look at them when they are sleeping or walking around, getting dressed and so on. Still, if we can use cameras to detect if someone falls down to the ground, maybe they have a heart attack or falls out of bed, it's very good if we can send an alert to some nursing staff. Also applicable to public infrastructure, such as metro stations where lots of people are moving around. It's, of course, good if you can detect if someone falls down to the ground for health issues or violence or whatever. And training data access in these facilities is difficult. Obviously, you cannot just record people sleeping in elderly care centers. So I'll talk a little bit about how we handle that. First, a video illustrating the concept. So this is applying human pose estimation on a person. This is an acted scenario, of course, because we cannot really show real scenarios. But using human pose estimation, it's quite easy to get accurate estimations of where people have their heads and feet and the knees and so on. And from that, we can make some kind of estimate if they're standing up or lying down and sitting down and so on. So our initial algorithm idea, to give you a sense of how we work with algorithms as well, was to just use this pose estimation and then apply some post-processing on the pose data. So since this pose data itself is quite anonymous, we can get training data by collecting anonymous pose data instead of collecting raw images. And then we can use this pose data to train like secondary methods to figure out if someone is lying down or standing up. The problem with this approach was when we got one of our first reality checks, we encountered cameras with quite low quality. For example, these ceiling-mounted fisheye cameras that were actually used in some elderly care centers. This is again in our office because I cannot show real images, but it looks a bit like this. So roof-mounted fisheye cameras, has to work at night when there is low light, which leads to long exposure times with motion blurs and typically quite low bandwidth, high compression. And as you can imagine, it's quite difficult to make an accurate pose estimation of an image like this. Furthermore, it's quite an intrinsically difficult problem to solve. Even if you have an accurate pose, how can you just from the pose data tell if this person is lying down or standing up? So what we did was instead use entire image data, because there are actually image or visual cues in the image that you don't capture with the pose. For example, due to the perspective here, if the person is standing up, his head would be larger than his feet. And if he would be lying down, it would be the other way around, maybe, due to this perspective. So this pose skeleton doesn't really capture that, but looking at the original data, we can capture that. So we decided on training a full object detector directed from image input to sitting, standing, lying person. Still, problem remains, how do we get access to training data? Because now we suddenly need raw data again. Well, unfortunately, we have no silver bullet, but what eventually worked out for us was to use a combination of lots of different approaches. So we built our own photo lab with some cameras with representative angles and invited lots of people to walk around in this lab, lying down. We had these like pizza parties where people can come and hang around, lie down a little bit, sit down a little bit, and with full consent, of course, with everyone involved. We also did some images from our own homes. This is actually my home in the middle here, so to get good variation with lots of cluttered backgrounds and different lighting and so on. And finally, we did lots of 3D render data. So using a pipeline consisting of Blender that is scriptable from Python, it was actually much easier than I expected to get this 3D rendering started. So in the bottom here, you can see some artificially created views where we can move around furniture, we can change the lighting, we can apply noise, downsample to low resolution and so on, and make quite varied scenarios. And the conclusion is that the combination of all this was needed to get the accuracy that was required. So not a single one of these data sources were enough, but the combination solved the problem. Second aspect of privacy is real-time anonymization that does not deal so much with training data, but rather with the operational aspect of our system. So some examples, again, this fall detection in elderly care. If some person is falling into the ground at night, it would be useful to send some kind of visual information to this nursing staff, but we don't want to show someone walking around in their living room without clothes. So can we do something that includes some visual information but still respect the privacy? Another example is occupational safety in wage management, where we had a project where the customer was interested in monitoring these waste trucks driving around with the waste on them. Sometimes this waste would fall off, creating an occupational hazard because there would be like waste bags lying around where they would be driving. But since the purpose of this surveillance is monitoring the cars and the waste and not the people, According to GDPR and things like that, they actually need to consider the privacy aspects. So if the personal data is not needed, then it should not be included, if it's not essential to solve the task. So we have this approach where we can apply an anonymization filter to video that runs in real time and can be used in lots of different scenarios. So this is, again, the simulated or acted scenario from the fall detection. You can see that even though it's pixelated, you cannot really see which person it is. You still get some kind of feeling about what happens. And this is a more like traditional outdoor security scenario. Still impossible to know who it is, but you can get some kind of sense about what happens. This is actually used by several customers in different locations for stuff that are more sensitive. How this works, it's unfortunately the time is too limited to go into details, but just a rough overview of it is we have this like background modeling, which is a classical computer vision approach to detect what is background, what is foreground. We have a really efficient human detector that can detect humans, and these are combined in like, let's say, clever engineering ways to make sure that we don't need to run the human detector every frame, because then we could not handle the workload that we have. The combination of these creates a mask, which is basically a non-zero mask. It's non-zero where we should apply the anonymization, and then we have this final pixelization filter that just sort of replaces the original image with this pixelized version where it's needed. Key features to make this fast, we can run this on 10 to 50 video streams on a single server in real time. And the key features is don't run everything at once. So it would never work if we just throw deep learning on everything. So run deep learning when it's needed, run some cheaper methods when that's enough. And another key is to have a really good human detector, which needs to be efficient and accurate. And of course, the key to get a really good human detector is to have really good training data. And with good training data, I mean bad training data. So over the last 10 to 15 years, we collected real-world data from lots of different installations with low light, high compression, noise, low frame rate, occlusions, everything. So it's much more noisy and dirty than any data you would find on public data sets. Final aspect of privacy that I will mention is how we think about edge processing. So our system runs in the cloud most of the time, but we can also run stuff in the edge when needed. And the motivation for considering running stuff on the edge instead of the cloud is this gray zone that is it really acceptable to run personal data in data centers owned by American companies? Even if we use Microsoft Azure or Google Cloud located in Europe, it's still an American company that owns everything. And there is some kind of legal potential right from the American government to ask for data from these companies. And even though Microsoft says that, yeah, we will defend any such requests, we don't really know. So it's a gray area. And some companies prefer to play it safe and say that, okay, we don't want our footage in the cloud at all. We want it in our own on-premise networks, even sometimes air-gapped networks that are completely disconnected from the internet. So, of course, there's also internal company policies, public opinion, and so on. So our approach here is to try to support everything. So people that want it in the cloud can have it in the cloud because it's convenient. People that want it on servers on their premises can do that. And people that even want to run algorithms in the cameras can do that, because then, for example, in this elderly care situations, you can have an application where you have a camera looking for people falling down to the ground, no footage ever leaving the camera at all. Just a signal that, oh, someone is on the ground now. So that would be kind of the most privacy-friendly way to do it. To enable these edge processing stuff, we spent considerable efforts to squeeze in as many cameras as possible on a single server. So a little bit about edge inference, how we work with optimizing that. 3 different main tricks. So one of them is really try to make small deep learning models. Instead of adding more and more layers, we try to remove layers to make them as efficient as possible. The reason that this works quite well for us without sacrificing too much accuracy is that the hard cases are quite low resolution anyway. So, I mean, we can classify people down to something like 20 pixels high. And if we have that few pixels, we don't need these really large networks. So we have experimented a lot with minimizing the network architectures, and now have a pipeline which is very fast. Also, we run it on CPU instead of GPU because that makes it easier for customers to select any server they want, and also makes it easier to squeeze into cameras. We run quantized models using OpenVINO, and I can recommend looking into OpenVINO as an inference framework for anyone that wants to run it efficiently on CPU. I think it's good. And finally, we run a combination of classical computer vision and deep learning in order to make this as fast as needed, because deep learning, if we would just apply deep learning on every frame, it would still be too slow. So really efficient, optimized background models combined with running deep learning when it's needed. And as a result, we have a primary deep learning model that classifies persons and vehicles, motorcycles, and so on, that can classify something like several thousands of patches per second on the CPU. And this is not run all the time. It's run whenever needed, and the final system can support something like 10 to 100 video streams on a single server. And this large range, 10 to 100, of course, depends on resolution, it depends on frame rate, it depends on the exact server model, and so on. Usually we end up somewhere in the middle, so maybe something like 50 camera streams on one server, running in real time and giving alerts within 5 seconds. Most of our algorithms can also run embedded in cameras, which then usually use Linux and ARM CPUs. Sometimes they have some kind of accelerator chips and so on, but we try not to use them because it tends to be very specific for a very specific camera brand. So, take-home message. 3 different aspects of privacy in our business, and I encourage everyone to think about these terms. So, for example, if you have problems with training data, use a combination of everything. Use acted scenarios, use 3D modeling, just throw in whatever you have. Anonymize what you can, whatever that means to you in your business. If you don't need personal data in production, don't use it. Yeah, use what you need. And don't be afraid to push processing to the edge. And use CPUs, they are better than you think. Thank you.
Thank you, Erik. Yeah. Very interesting and an important topic. You hear stories about security firms looking at videos. All right, are there any questions?
Yes, we already have questions.
Thank you for the talk. I'm Aslı Röddin from Volvo Cars. I was thinking about anonymization and wondering if you have tried any other images than RGB images. I'm thinking infrared, where you don't see any faces, but you still get some sort of body figure. I know there is no training data set, or at my knowledge, but you already are collecting your training data. Could it be, I don't know, have you tried it?
Yes, a very good question, and the answer is yes. So we typically work with whatever cameras the customers already have, and we connect our analytics engine to it, and many customers do use infrared cameras. And if they have that, then we support it, and then of course anonymization is not really needed because these images are already anonymous. So we have a separate training data set for infrared where we can classify things like people and animals and try to be specific also there. So yeah, but we don't force anyone to select a specific type of camera. Usually they already have hundreds or thousands of cameras mounted and they don't want to replace everything.
Do we have more questions?
Down here on the left.
Thank you. Thomas Björklund, also Volvo Cars. Question about classical computer vision. Can you be more specific there? When you don't use deep learning, what are the classical methods that you would recommend?
Yeah, we have a large range of different methods that we combine, actually, but the most obvious thing is background modeling. So in many of these classical surveillance scenes, usually not much happens. So just by having some kind of background model, we have experimented with different approaches, and the one we selected is kind of secret, but just finding out where something happens that sticks out from the background helps a lot. And then we have different stuff. For example, we have monitoring functions for monitoring if a camera is shifted a little bit, because if a camera suddenly is shifted 30 degrees, then of course some thief can sneak in and do some stuff in the dead angle. And we have methods for that as well, like tracking-based methods that can know if the camera angles is fixed or not, regardless of time of day and weather. And so it's more difficult to do that well if it can some day snow, some day rain, some day, So finding the shift, but not finding the other stuff.
Okay, so still unconventional, but classical. Or
Yeah, combination of conventional stuff, but background modeling, I would say, is the main thing that sort of saves most CPU time.
Hey, I'm Praful Mishra, also Volvo Cars. First of all, great work, but I was just curious, you talked about sending models and moving to the edge, essentially, to the edge computer devices. Are you also using some sort of federated learning to kind of get in the more training data to kind of improve from those edge devices, I'm assuming?
Good question. Currently, we don't use federated learning. No, we are looking at it, but we haven't started to use it. We can collect data from most places that are connected, even though the processing is on the edge. We can sometimes collect data anyway. And the hard cases are usually these very far away people with very low resolution, where privacy is not really an issue because the data quality is so bad, so you couldn't identify the person anyway.
Okay, thank you.
I think we have a question from down here.
Where?
Did you raise your hand? No. Okay, we have,
We have a
one
question there.
I was so happy. It looked like there was another company than Volvo who were asking questions.
Yeah. Hold on, I just forgot my question. No, I really forgot it. Yeah, could it, I'll ask for it again in a minute.
Okay, we have one more.
Hi, Dirk Koppling, not from Volvo Cars,
Yes.
but Ericsson. The example you shown for privacy, face recognition, you disabled to recognize the face, but when you are in private homes, for example, so isn't privacy, the home is privacy. What's your view on removing all the furnitures or any that size sign-off you can identify within the apartment, for example?
Yeah, so I mean, for example, if we would have a surveillance in someone's home and then sending anonymized clips, removing the entire background and everything.
Right.
Yeah, I mean, first of all, we don't really have any, I would say, business in people's homes like that. We have these elderly care centers a little bit, and the homes are quite standardized. They have the standard bed, standard desk, and so on. So that is not. It has not really been an issue, I would say. I mean, we could do it, but no one has really asked for it.
Maybe follow up on this. The GDPR, is there a conflict there, or is this in line with GDPR? Or do you see other initiatives for privacy protection from a legal point of view, which maybe interfere with revealing, like in flats or in apartments, details?
So I didn't really get the question. Sorry, can you repeat?
The legal framework,
Yes.
like GDPR,
Yes.
or maybe other initiatives coming up on protecting privacy. Is there anything you can?
Yeah, I would say
comment
that in Europe, I mean, GDPR is the main thing. In Sweden, we have this kamerabevakningslagen, camera surveillance regulation, that is a little bit in contrast to GDPR. It's related, but it also says that governmental agencies require a camera permit to do surveillance at all. And so, for example, schools and different kinds of authorities need permits to do it if they do any kind of personal data processing within the video. But if it's not for actually identifying people, then they don't need the permit. And that is sort of a Swedish legislation, which is a little bit outside of GDPR, but still applicable. I would say those are the kind of main things in Sweden, at least. Then there are certainly different variations in different countries, but I'm no legal expert. So.
Right, I think we'll...
Oh, someone remembered.
Hi, and thank you for a great talk. My name is Henrik Rodin, and I am not at Volvo Cars. I'm at AFRY, Future Tech. And my question relates to how you find that they're lying down, or this pose estimation. That when do you know that someone has fallen down? And you were mentioning the different kinds of data, and you want a good but bad data, and all these other aspects. Are you looking at the context within which the person is in the room? So you're looking at the whole room to figure out how the posture is related to the room? Or are you looking at the distortions or like angles and these things for the body itself?
Good question. I mean, we started to look at the pose data, and then it was obviously just the sort of main orientation of different body parts. We found out that that was not good enough, so we switched to this detector-based method where we actually train a detector to look at the whole image and give out bounding boxes of people lying down. So you would have to ask the neural network what it actually looks for. But it takes image in and gives us boxes, and those boxes are good enough.
It sounds like there's context. Thank you.
Right.
Thanks.
Yeah, one more.
Hi, Alessandro from Ericsson. My question is, have you ever had to deal with adversarial attacks? And if so, how robust is your system?
Good question as well. We haven't looked much into that. We haven't had any suspected case of anyone trying to do that. I would assume that, I mean, if someone would try to break in at some facility having some sign with some stuff on it, I expect it not to work. I mean, I expect our system to work and expect the attack to fail, because the video quality is usually very poor, so having some kind of sticker on your jacket or whatever, I think it would just not really be visible enough. Of course, if you dress as a giraffe trying to enter some facility somewhere in Africa, that might work. But no, we haven't had any trouble with it, and no main requests for it.
Yeah, let's go.
Hello, I'm Erik from Cellink, and I was wondering, when you do classification or detection, you always have a risk of either in the case of someone falling over, that detecting someone has fallen over when they haven't, or you don't detect them when they have fallen over, and there's a cost associated to mislabeling both cases. How did you proceed, or how did you reach a compromise between how to compare these two costs?
Yeah, I mean, in most cases, a false alarm is better than a misdetection. In almost all cases. That being said, false alarms cannot be too high either. So, for example, we have a really, in some cases, we have very many nines in our accuracy. So I can mention this Stockholm subway, for example. They have bought 400 licenses for our system, and they have this kind of central where people receive alarms. And if one camera would send one false alarm per day, they would get 400 alarms per day, which would be something like 20 alarms per hour, which would just be noise. And that is way too much for them. So having something like maximum one false alarm per day, when you have 5 seconds to react, that actually translates to a 99.99% accuracy. So it needs to be very high, even if occasional false alarms are better than misdetections.
Okay, great questions, great answers, and yeah, let's thank Erik once again for this talk.
Thank you.
Thank you very much.
Yes. Yeah.